welcome to this afternoon session. Our next speaker is Katz. So I looked up a little history on his Wikipedia page, and it apparently looks like he earned his bachelor's before he was of voting age, and his doctorate before he was of drinking age, which makes sense if you know what voting age and drinking age are in the US. But this was a while back. He has since done some great work in mathematics and was awarded a Guggenheim Fellowship in 2012. He is now at Caltech, and he will be speaking today on Flecnode polynomials and incidence geometry.
Okay, well, thank you for that nice introduction, and I'd like to thank the organizers for inviting me to this beautiful conference. I feel a little out of place here, and I feel my talk is going to be a little out of place. There will be no formal power series, and whether it's combinatorics or not, people sometimes argue about. But I'm going to basically survey some recent developments in incidence geometry, especially in 3 dimensions, and try to point out what's kind of the central object in those developments, and maybe make a few suggestions for what will happen about the future. Of course, suggestions about the future are usually wrong, but you guys can make them improve. Okay, so first of all, I should say what incidence theory is. So we'll be talking about incidences usually between points and lines, and usually in R3. So you have some set of lines around, you have some set of points around, and an incidence is a pair consisting of a point and a line where the point is on the line. And what we'd really like to do is count those, maybe not quite in the sense of this conference, but we'd like to up or down the number of those. We'd like to know that somehow, given a set of points and a set of lines, they don't lie over each other too much, more than is proper. There are various motivations that have been around for a while for studying this, and what your motivation is might depend on what kind of a person you are. I think of myself as an analyst, and as an analyst, my motivation largely comes from the Kakea problem. I'll tell you a little bit about what that is, which will maybe really get people in this conference unhappy. And the more combinatorial motivation was the study of Erdős's distinct distances problem, which I'll also talk a little bit about. But I wanted to start out the first slide with a famous old theorem in incidence geometry. This is the theorem of Semredy and Trotter. It's a theorem about the real plane. And it says that if you have n distinct points and m distinct lines in the real plane, there are at most O of n to the 2/3, m to the 2/3, plus n plus m incidences. The way you should think about this is that when n and m are about the same size, where by about the same size I really mean the first term dominates the last 2 terms, then it's really the first term you should be looking at, and it's the exponents in the first term that are important. And these exponents are actually typed. You can produce examples that have that many incidences, and we know that up to constants there are no more. So this was discovered by Semredy and Trotter in 1983, and I should emphasize this is a theorem about the real plane. If you, say, considered the plane over a finite field with p elements, then you have about p squared lines, you have about p squared points, and the number of incidences is about p cubed, because there are around p lines through each point. And so what you see then is that you would need exponents that were like 3/4 to capture this. So this is something that's true about the reals and isn't true about finite fields. And it's actually a theorem about topology. It's It's a topological theorem. And the way you might first encounter this, if say you were teaching, is that you might be teaching about finite geometries like the Fano plane, and you might start to, draw the Fano plane. People do this. And they try to draw it in such a way that there are as many lines as possible that are real lines. So here I'm drawing the Fano plane. I have 7 points. I have 6 of the lines, and those lines are all lines in the plane. I've sort of almost embedded the Fano plane in the plane. And then there's some topology, of course, is the last line, not really be a line. There's a line in the Fano plane that contains these 3 points. And what Semrety and Trotter captures is this topology in a quantitative way. Okay, so my own interest in this subject originated from the Kea problem. The Kea problem asks how small can a set be in Rn if it contains a unit line segment in every direction. This question was first asked in the plane by the Japanese mathematician Kakea in the 1920s. And the real question you should be asking yourself is, what on earth do I mean by small? And Bezukovich, late in the 1920s, showed that there's a set in R2 which has 0 measure. I leave the comment, is that interesting? And from our point of view, well, for this lecture, which is the study of incidences, I'm going to argue that that's actually an analyst's theorem, and it's not quite so interesting, and I'll tell you a little bit about how it works. But a main open question, which is for dimensions greater than 2, is whether such a set has to have full Hausdorff dimension. That's, I guess, also an analyst's question, as stated. I'm not even going to bother you by defining Hausdorff dimension. And we really know amazingly little about it. In dimensions 3 and 4, the best lower bound is due to Tom Wolfe, n plus 2 over 2, okay, 5 halves in dimension 3 and 3 in dimension 4. Actually, in higher dimensions, it's been improved. I'm not here stating the best current known results, and what I've written there beats this in dimension 8, but there are some intermediate results that combine ideas. Anyway, the main idea behind Wolff's argument is very simple. It's that triangles always lie in planes. So if you take a lot of lines that intersect a given line, Wolff called this a hairbrush, then those lines are divided into separate planes, and you can kind of study this problem in the plane. And then if not all the lines meet in a single line, well, you have some lines that don't intersect, and that's good for things not to be too overlapping. So I think I was going to tell you a little bit about why the known Kakea sets aren't interesting. So I was going to describe Bezukovich's set in the plane, and not really in the way that Bezukovich did it. If you've ever looked at this, you've probably seen some pictures. You start with a triangle, you cut this triangle in half, you move the 2 halves a little bit so that they overlap somewhat. And then you keep doing this, and you obtain some sort of a fractal, and you make an argument that this fractal goes to area 0. I actually like a more algebraic kind of description of it. So what you can do is decide that you're going to write down a bunch of unit line segments in each direction, and I'm not really writing down all the directions, I'm writing down n to the n directions. So I take n to the n slopes that are between 0 and 1, that are rational numbers with denominator n to the n, and I write these in n-ary expansion, so that's what these AJs are. They're the digits in n-ary expansion. And for each one of those, so so the first displayed formula up there is the description of a slope, and then I need to tell you what is the y-intercept that's going to go with the slope, and I'm going to just draw a sort of rectangle that's width 1, width 1 over n to the n, and projects down to the x-axis with length 1. And I have to tell you where is the y-intercept. And I write down a very similar looking formula for the y-intercept, except that it's not really an n-ary expansion because the numerators aren't between 0 and n anymore. But so basically what I've done is that I've multiplied each term in that series by minus j over n, where it's the jth term. And what that does is that when you write down the equation of the line, which is y equals mx plus b, what happens is that when you plug in j over n, the jth term in the series for mx plus b vanishes, which means that around the x position j over n, you've grouped these slopes into groups that have the same first j digits, and there are actually fewer groups like that than you would think. There are only n to the j minus 1 groups because you don't care at all what the jth digit is. So what happens is that you gain a factor of n from this. I think I'm skipping ahead of my slides. And the conclusion is that the union of these rectangles, okay, they're not really rectangles, they're parallelograms. But anyway, the union of these rectangles has area of 1 over n. And so if you take some sort of a limit as n goes to infinity, you can, in some way or another, get to 0. And up to logs of n, this is actually sharp. This is the best you can do in the plane, and that's a result of Cordoba or Cordoba-Pfefferman or Pfefferman. It's a little bit mysterious who knew what when, but in the 1970s, harmonic analysts were really interested in this kind of thing because the Kakeya problem has some implications about problems in harmonic analysis, problems about Fourier multipliers. And then the question is, are there any interesting Kakeya sets? So one thing I should have said is that, there we had n to the n directions. We had discretized to thickness 1 over n to the n, and all we got as far as the smallness of the Kakeya set was that it was 1 over n, and the way you should think about it is that the dimension was still full. It was measure 0, but it had full dimension. And the question is, can you get really interesting Kakeya sets which aren't just having this trick where somehow each digit is a scale, and so there's a different position where each digit doesn't matter, and there's a multi-scale phenomenon. Instead of this kind of multi-scale phenomenon, can one find really genuinely a situation where lines and points are interacting in a really clever way? In some sense, the example I showed you had to do with rectangles. It didn't have to do with lines and points at all. It's just that you got to think of the rectangles with different thickness in different places. So Wolf proposed a model problem for this, which was in a finite geometry. This was the n-dimensional space over the field with p elements. So now we're in combinatorics, right? That's a finite space. And lines are finite things too. And the question is, how big how small can a set be if it contains a line in every direction, just a line over the field FP? And this problem was solved by Dvir in 2008. I should tell you that this had a long prehistory, so Wolf posed this in the mid-90s, and then many people wrote papers which kind of mimicked all known arguments about the Kakeya problem. But no one made any progress. No one had really better exponents for this problem until Dvir. And Dvir, spectacularly in 2008, completely resolved this model problem. And moreover, he one-page proof, which maybe will look more natural to you guys than it did to me or to the crowd that was working on the K problem. So Dvir's idea.
Okay, can you
Sorry.
go back once again?
Sorry, so I should say something about this inequality. So I was using OA before, and this inequality with a tilde sign means that there's an implicit constant, and that constant is allowed to depend on n, but it is not allowed to depend on p, and this is somehow the point. And Dvir's idea is you just find a polynomial, a multivariate polynomial, which vanishes at every point on the stochastic set, and you find this polynomial with degree as low as possible. How do you do that? You count how many points you have to vanish at, and you count how many coefficients does a generic polynomial of a certain degree have, and then when the number of coefficients is larger than the number of points, you can find such a polynomial. So if you were a lot smaller than p to the n, if your k set is a lot smaller than p to the n, you find a polynomial whose degree is lower than p, a non-trivial polynomial whose degree is lower than p, which vanishes on the k set. And you take this polynomial and you write it as a sum of its homogeneous parts, where obviously the highest degree homogeneous part has to be non-zero, or else that isn't the degree. And then you observe that your polynomial has to vanish on all these lines. So a line is a point x plus a parameter t times z, where z is the direction of the line. And you say, all right, so my polynomial evaluated on that line is a polynomial of degree d and t, and it had better be the zero polynomial since it's vanishing on that line, which means that the highest degree part of the polynomial evaluated at the direction is 0. And since you have a line in every direction, it means that the highest degree part of the polynomial vanishes at all points. Now, of course, we're in finite fields, so you should worry a little bit, but the Schwartz-Zippel lemma says that if you have a polynomial that's of degree much less than p, it's not going to vanish at all points. This is basically an inductive version of the fundamental theorem of algebra. I think the degree 1 version is just the fundamental theorem of algebra, and then you induct on dimension. So we've reached contradiction. This is the one-page proof of Dvir's theorem. So all you do to solve the K problem in finite fields is that you just find a polynomial that's vanishing on your K set, and you see that it's crazy, it can't exist. So this was completely new to people in harmonic analysis, and it was also completely new to people in incidence geometry, and we were all really in a hurry to see if we could adapt this to what we thought of as the real problems. I guess in this case it's a pun. Real problems are problems over the reals. So now I'm going to write down a result in 3 dimensions. This result is implicit in work of mine with Larry Guth in 2008. We were trying to solve previously stated problems. So there was a problem called the joints problem and a discrete version of the K problem that this theorem solved, although sort of separate parts of this theorem solved each of them. And it was explicitly stated, as I'm stating it here, by Elkish and Sharir in a very important paper in 2009. But anyway, let's say you have a set of n-squared lines in R3. I want to emphasize that this is a 3-dimensional incidence theorem, and you should be a little worried about how can 3-dimensional incidence theorems be any better than 2-dimensional incidence theorems. After all, if we have an arrangement of lines and points in R3, we can project them down to a plane, and that only increases the number of incidences, which means that Simonetti-Trotter still holds. and at the same time, maybe all the points and lines are in a plane, so we can't do better. But of course, the point is there are going to be some hypotheses that say that really this isn't happening in a plane. And what you should be watching for, maybe for the rest of this talk, is hypotheses of three-dimensionality. They're going to appear in different ways. But in this situation, our hypothesis is that no more than n of these n-squared lines line a plane. And now P is going to be the set of points where at least 3 lines intersect. Then that set of points up to constants is no bigger than n cubed. So this solved a couple of conjectures of medium standing, and it was a kind of first adaptation of De Vere's proof to real incidence geometry. So how does it work? Well, again, it's going to use this De Vere idea. We're going to try to find a polynomial which vanishes on all of these points, and hopefully it's going to be of low enough degree that it will vanish at most of the lines, because if you have a polynomial of low degree that vanishes on more points of a line than its degree, then it vanishes on the whole line by the fundamental theorem of algebra. So this is kind of a recipe to have it vanish on a lot of lines. So what we'd sort of like to see is that the whole setup is in the 0 set of some multivariate polynomial of not overly high degree. So what happens if that set of points was too big? What if it contained a lot more than n cubed points? So q n cubed with q a large number. How low degree a polynomial can get all those points in the 0 set? So if you do what I did a few minutes ago, you count the number of points and you count the number of coefficients in the polynomial, you don't get a happy answer. The answer that you get is n times q to the 1/3, more than n. It turns out that n is a kind of very critical threshold here, and one wants to get a polynomial whose degree is smaller than n. But in fact, one can do this by being slightly clever, because what we're not using when we just count points and we just count coefficients of polynomials, we're not using the fact that these lines are all crossing each other quite a lot. There's some kind of illegal, overly optimistic crossing that happens if there are qn cubed points where 3 lines meet. And so one can do better than the first guess, and in fact one can get something substantially smaller than n. I don't think what I've written is sharp. I think the sharp thing is actually n over q. I get kind of sloppy when I try to write this argument quickly. So the idea is you just pick a random selection of the lines. You don't pick all of the lines. You just pick some proportion of the lines. Probability 1 over q works. Again, I don't think that was the optimal choice. So typically a line here in the original setup would intersect qn of the point of the other lines, so that there would be qn cubed of these points. And here what's going to happen is that it'll intersect n of the lines that we picked. And now we just need to find a polynomial which vanishes on the lines we picked. And here we get to use the coefficient counting argument again by just selecting the appropriate number of points on each line. If you just select n over square root of q points on each line, you can get some polynomial that vanishes there. And I guess I didn't write any more on the slide, but the conclusion is supposed to be this conclusion that you get a polynomial of quite low degree. So we call this argument degree reduction, because you have a lower degree polynomial than you imagined just by counting. So now what we're going to do to prove the theorem is that we're going to use Bezout's lemma. Bezout's lemma is maybe most familiar in the plane, where when you two polynomials of degree m and n, and their zero sets contain more than mn plus 1 points in common, then there's a common factor. But here we just extend this to 3 dimensions. If you have two polynomials which are 3-variable polynomials and they have mn plus 1 lines on which they jointly vanish, then again these polynomials have a common factor. You just check this by taking cross sections. You find a common factor on each cross section, and that implies there's a common factor on our fleet. And so now one of the polynomials is going to be this polynomial that we've just found, whose degree is under control by n. And then what happens? Well, we're going to now imagine, I'm leaving out details, as I think I'll do for the rest of the talk, but we'll imagine that this polynomial f has already managed to vanish not just at the points, but on all the lines, and in reality it's on most of the lines. And then these lines are meeting 3 at a point, and there's 2 ways it can happen. One is the way I've just drawn it, that these 3 lines live in a plane, and then the other is the way that I can't draw it, which is that the 3 lines are not coplanar and therefore not on the chalkboard. And in either case, something very weird has happened. So these 3 lines are in the 0 set of the polynomial. If they weren't in the plane, that means that that 0 set doesn't actually have a tangent plane at that point, so it means that the gradient vanishes. And otherwise, if they are in a plane, this actually means that the second fundamental form vanishes at that point, because if you take a quadratic approximation to the polynomial at that point, then the 3 lines are in the 0 set of that quadratic approximation, and they're also in the 0 set of the plane, and by kazoo, therefore the plane is a factor. So you have either the gradient or the second fundamental form vanishing. You decide which one happens more often. You have to do some arguing to say that for the one that happens most often, a lot of lines are still in the 0 set, which just involves counting, and then you get to apply kazoo to this. And this is basically the end. If it's the gradient, then if I started with a square-free polynomial, I don't have any common factors with the gradient. And if it's the second fundamental form, by the time I get to the second fundamental form, that's a slightly higher degree polynomial. You might argue it's not a polynomial because it has some square roots in the bottom, which I'm just ignoring. But in any case, if the polynomial has this relationship with the second fundamental form, then it turns out that too many lines lie in a plane, and that was one of our hypotheses. And so that's it. And you should definitely notice that we seemed, for this argument, to need 3 lines meeting at a point. Okay, so my more combinatorial motivation was the Erdős distinct distances problem, and now I'm going to remind you what that is and tell you what it had to do with the theorem that I just proved. So in 1946, Erdős asked, how many distinct distances must there be between endpoints in the plane? And a square root of n by square root of n square lattice has about n over square root of log n distinct distances, basically because not every number is the sum of 2 squares, and we know which are. And people wanted to show that, well, Erdős wanted to show that this is the best example, but getting lower bounds was a little bit harder to do. But in 2010, with Larry Booth, we proved that there are at least, up to constants, n over log n distinct distances, which comes very close to matching. It's an almost sharp result, if you will, if you don't care about logs.
Excuse me.
Yeah.
Do you assume no 3 on a line?
No, I don't.
If I put all of them on a line, don't I get
There are n minus 1 distinct distances at least. You take one of the points on a line and, yeah. Okay, so that's actually an easy case. The one-dimensional case is slightly easier, but no matter where they are, they have to have at least n over log n distinct distances. So the first thing I want to tell you about this is, what does that have to do with incidence theory? What does that have to do with incidences between points and lines actually in R3?
So actually, did Erdős ask for a lower bound or also for
Both.
an average? Both.
Oh, average. No, I don't know what you mean by an average. But he asked.
Take a random configuration.
If you take a random configuration, it's pretty clear that you have n squared distances, right? Because there's just no reason in it
So it's a lower
to
bound.
be the same. Right, so he was interested in the lower bound. He was interested in some other related problems. But in any case, what I want to talk about now is what this has to do with points and lines, and particularly with points and lines in free space, where the Erdős problem is, as stated here, is in the plane, but it's related to incidence theory in 3 dimensions. So this is an idea of Erdős. He wanted to study Erdős's distinct distance problem, basically following the Erlangen program. If we want to do a problem in geometry, we should do this problem by looking at the group of symmetries of the geometry. The group of symmetries of the Euclidean geometry in the plane are the set of rigid motions. And this whole problem should take place in the rigid motion space, which is 3-dimensional. The rigid motions of the plane mostly consist of rotations about a point. There are a few rigid motions that are translations, but those are rotations about points of infinity. So we really need a good coordinate system to think about this. So you need to know the center of the rotation, and you need to know the angle of the rotation. So the rotation has a center AB and an angle theta, and the coordinate system I'd like to use is AB cotangent theta over 2. That may look very strange. It doesn't make any sense if theta equals 0, which is exactly the translation case. But for the rest of them, this gives a nice map into R3. And what's good about this map is that if you consider 2 points in the plane, and you ask, what are all of the rotations which send P to Q? Well, we know something about the center of those rotations. The centers have to lie on the perpendicular bisector between P and Q. And then we can ask, what is the significance of this angle? Well, here's half of the angle, and you see that how far along this line we've gone to pick the center is proportional to the cotangent of half the angle. So when we pick this coordinate system, the set of rigid motions taking P to Q is exactly a line. It's an honest straight line in this coordinate system. And we're going to look at incidences between those straight lines and points. What do they have to do with anything? Well, if you have few distances, that means that there are many pairs that have the same distance. So there are many, what I guess we call distance quadruples. 4 points are a distance quadruple if they have the same distance. I think I took my joke out of this slide. My joke is that the ancients called these pairs of congruent line segments. But so anytime you have a pair of congruent line segments, there's a rigid motion taking one to the other, which means that 2 of these lines, LPQ, are intersecting. So if n points in the plane have d distinct distances, there have to be at least n to the 4th over d distance quadruples. So if you can show that there are not a lot more than n cubed distance quadruples, you've shown that there have to be a lot of distinct distances, and that's basically the game you play. But you have to treat separately. I mean, so this is so far what I've kind of done for you is turned the problem into a problem about lines in space and their intersections, and I want to turn it into a problem about incidences between lines and points. And if you have, points are now rigid motions, but now if you have k lines that meet at a point, they produce k squared quadruples because they produce k squared pairs of lines that intersect. So we need to treat points differently depending on how many lines are meeting at them. And if we could show a bound that's like n cubed over k squared for the number of points with k lines meeting at them, well, we get the theorem. We get, with theorem, the log comes from the choices of how big a number k is. I really don't care about k up to the factor of 2, so I really lump together all the points that have between k and 2k lines, and then I have log many of these sets of points. So that's all we have to do. We have to get this kind of a bound, and you notice that there are n squared lines. If we started with n points p, with n p's, then there are n squared LPQs, so we have n squared lines, and this looks a lot like the theorem that we had before. Maybe this is a moment to go backwards. The theorem that we had before had an n cubed in it. Of course, it was an n cubed for points where 3 lines were meeting. So we've got this completely under control where k is 3. But then there's an issue, you know, what happens when k is large? What happens when k is 2? So here's a reason to be pessimistic. The reason to be pessimistic is that that we can't just do algebra. I mean, at some level, the theorem before was almost just algebra. There was a little bit of geometry involving the second fundamental form, but basically it was about comparing polynomials. And that won't entirely work. Again, for the same explanation as what I gave for why the Summeray-de-Trotter theorem doesn't work in finite fields. Namely, if you work in a 3-dimensional space over a finite field and you take all the lines and all the points, they have more incidences than are allowed. So here I'm just explaining why that's more than are allowed. And so to get this result, we actually have to use some topology. I'm going to spend a little time explaining how that topology works. So it's a sort of modern approach which really uses polynomials in the topology, and the polynomials are being used, among other things, to give a quantitative description of the dimensionality of the set of points. We really want to distinguish between sets of points that are on a low-degree surface and sets of points that are genuinely 3-dimensional. Basically, given any number of points in R3 and a number capital Q, which I just fixed, there's a polynomial whose degree is around m over q to the 1/3, so that each component of the complement of its 0 set contains at most q of the points. So this is actually a consequence of the Borsuk-Ulam theorem. It uses something called the polynomial ham-sandwich theorem. The polynomial ham-sandwich theorem tells you that given some number of sets of points, you can find a polynomial whose degree is so that it has roughly the same number of coefficients as the number of sets of points, and so that the polynomial cuts those sets of points in half, as long as you don't mind that some of the points fall on the 0 set. So what you do is you cut the set you start with in half, and then you cut it in half again. You keep having to use slightly higher degree polynomials as you do this, and you multiply them all together when you're done, and you have you've divided up the points into sets of at most q, although it could happen that the points lie on the 0 set of that polynomial, and if they lie on the 0 set of that polynomial, it's a kind of quantitative statement that those points are not really in 3 dimensions. There's somehow close to being in a variety where close depends on what the degree is. So the way you should think about this is that I'm now going to tell you what happens if they're truly three-dimensional, which is what didn't work in finite fields and what this topology is gonna give you. And we'll just not worry too much about points that are on the zero set for a moment. So we suppose all of them are in the interior, and each line can meet at most as many of the components as the degree of the polynomial plus 1, because in order for a line to cross from one component to another, the polynomial has to vanish on it. And so then we look at pairs, which are lines and components, so that the line actually meets the component, and there's an upper bound on how many of those are. But there's also a lower bound, which I think I don't explain very well. So I forgot to say what Q was. You pick Q to be K. So you have some component where there are at most K points, and each point has K lines going through it. And if each point has K lines going through it, most of the lines don't meet more than one point, because 2 points define a line, and there are only basically K ways for one point to, for one line to meet a first point and a second point. Well, you just do some counting, and you see that you really have to have as many lines as you can here up to constants. You have to have about K squared lines. And that gives you a lower bound on how many line component meetings there are. And you immediately see that unless the number of incidences is below n cubed over k squared, this leads you to a contradiction. So that's good. If all the points were in the interior, then the topology has saved us. And what happens if all the points are on the zero set? Well, then we have all the points in the zero set of a low degree polynomial, and it turns out that our whole Bazoo machine works much better than it did otherwise. And so we're saved from what goes wrong in finite fields. And now what I've left out is what happens with points where only 2 lines meet. And what happens is that we get to use what's kind of the hero of this talk, the Flecnode polynomial. And the Flecnode polynomial was first discovered in 1850. It was published in a really beautiful book of the Reverend George Salmon, which is called Treatise on Analytic Geometry in 3 Dimensions. The world would be a much better place if every high school student, after finishing trig, would immediately read this book. It's a really beautiful book. And in fact, I believe that Salmon was a professor in Dublin, and he really used it in Dublin for approximately his freshman. And one of the things that he does in this book is that he describes his joint work with Cayley on ruled surfaces. And so what they found was that given a polynomial of degree n, there's another polynomial, it's Flecnode polynomial of degree 11n minus 24, so of degree not particularly much higher. You should notice that when n is 2, that's a negative number, but I really then mean that polynomial is 0 when n is 2. But for higher degree polynomials, there's this polynomial Fleck of f, and it vanishes at a point if and only if there's a line through that point which is tangent to order 3 to the level set of f. You just do your high school algebra, you find out that well, you probably decide to work over the complex numbers so that all polynomials have roots. I mean, all one variable polynomials have roots, and you discover that at a typical point of a surface, there are 2 directions where there's a line tangent to order 2, and of course there's a whole tangent plane of lines that are tangent to order 1, And typically you don't have any that are tangent to order 3, but there's a polynomial that checks whether you do. And then the amazing theorem is that this, that the zero set of f is ruled by lines if and only if this polynomial vanishes identically on the zero set. Another way of saying that is if you want to check whether a surface is ruled, whether a surface, an algebraic surface in R3 is ruled, you only need to take 3 derivatives. You take 3 derivatives along the line, which is the ruling. You get from that basically an equation, a PDE, that the surface has to satisfy. And if it does, it's all over. The surface is ruled. When you try to take the 4th derivative, the 4th derivative is sort of a derivative of the 3rd derivative. You just get automatically that it vanishes. So it's a remarkable theorem. It's a little bit messy to write down in any form, and it's even messier in the form that Salmon wrote it down in. So it's all written in coordinates in the most obscene way possible. And for this reason, people don't always like using this theorem. But anyway, it's really great for us because one thing that's already true just based on coefficient counting is that if you have any n squared lines, you take any n squared lines you want in R3, you can find a polynomial that vanishes on them and has degree O of n. But if it had degree just a little bit less, then we could apply Bezout's theorem to the polynomial together with its Flecnode polynomial. Remember that the Flecnode polynomial had degree 11n minus 24. The polynomial has degree n if you have more than 11n squared minus 24n lines in the zero set. It tells you that the surface has a ruled component. And this is really exciting because it says that in all the cases we've been talking about, the polynomials in question have actually been, I mean, their zero sets are actually ruled surfaces, or rather have components that are ruled surfaces. Anytime we got to use degree reduction, we got a degree that was lower than we expected, it meant there's a ruled surface around. We didn't really have to use that in many of the previous arguments, but that was kind of hiding from ourselves a glimpse of the truth. But to do the case of pairs of points, of lines which, points where 2 lines meet, we actually have to use this. So there are a couple of cases to consider. One case that you should consider is doubly ruled surfaces. There's only one doubly ruled surface in 3 dimensions, which is, one irreducible doubly ruled surface, which is the parabolic hyperboloid regulus. And if you had, n lines in one ruling of, n squared lines in one ruling of a regulus, and n squared lines in the other ruling, then they would meet at short points, and we would be in big trouble. But luckily, it turns out that our construction of these lines, the lines were LPQs coming from distinct P's and Q's in the plane, we can't actually have more than O of n of them in a doubly ruled surface. So the doubly ruled surface problem goes away. We only have to think about singly ruled surfaces. And there are different kinds of lines of singly ruled surfaces. There are the lines that meet all the lines in a surface, and an irreducible singly ruled surface has only about 2 of those. And then there are the regular lines, by which I mean the lines that are in the ruling. And those intersect only at most degree of the polynomial in many of the other lines in the ruling. And it turns out that from just that, in fact, the polynomial has a degree less than n, we get the bound that we want. So that actually was a sketch of the argument for the distinct distances problem. And what I wanted to do with the rest of my talk, I don't know if I have 10 more minutes or I'm supposed to stop right now, Okay, well, I think I'm only going to babble for about 3 or 4 more minutes. So I wanted to discuss some one open question and one sort of dream. So going back to incidences, basically what I'm saying here, I'm restating the theorem at the beginning that when you have n squared lines with at most n and a point in a plane, there are at most n cubed points where 3 lines meet. And I'm asking what happens when you're close to that number. So if you're above that number, if you're what the theorem excludes, then you can use all the machinery I've just said, and you discover that you can degree reduce, and you discover there's a ruled surface that the whole picture is living in. But if you have just slightly below this threshold where you can't use degree reduction, do you know anything? So there are a couple of examples that I know of such configurations of points and lines. One is when you just take n random planes and the lines are the n squared intersections between pairs of planes. Another example that I know is where you take an n by n by n square lattice and you take all the lines in coordinate directions for that lattice. And in both of those cases, you have a lot of lines lying in a plane. Does it happen in general? A lot of people have been asking this open question. Does it happen in general? Must there be almost n lines in a plane? And here, we're powerless because we don't have a Flecnode polynomial. We don't have anything that lets us get at this. If you were able to answer this question, you would actually have something kind of subcritical about points and lines. The last thing I wanted to do, which I guess I didn't leave myself too much time for, was to daydream about the Kikea problem. Should algebra say something about the Kikea problem? Can you understand algebra? Can you understand the Kikea problem using algebra? So first off, I wanted to give you a false cause for worry. Let's say you have a quadric polynomial in R4. So this gives you a 3-dimensional surface. This quadric is not only ruled by lines, it typically has a 1-dimensional set of lines at each point. An example you can think of is SL2. SL2R is a quadric polynomial, as a zero set of a quadric polynomial in R4, and it has a 1-dimensional set of lines through every point, which means that it contains a 3-dimensional set of lines, but those lines aren't all in different directions. So it's not a counterexample to the Kikea problem, although it's right at this n plus 2 over 2 exponent of Wolf. And in fact, Segre classified n plus 2 over 2 dimensional surfaces in n dimensions having n minus 1 dimensional set of lines, and they were either quadrics or they were rulings by affine subspaces. And there have been some further classical developments. R3, on the other hand, seems safe from toy examples because to get a toy example, the example should be a 5/2 dimensional Kikea set, and 5/2 isn't very much an integer. However, if you were willing to work over the complex numbers, there is a kind of toy example that shows up, which is 5 real dimensional and which has a 3-dimensional set of complex lines, which is a Heisenberg group. It's a 2 by 2 by 1 Heisenberg group. And it also has this nice, simple algebraic expression. It shows up a lot in work that's involved with trying to slightly improve over Wolf. So what could be a program for working on Kikea? Working on Kikea could really be something about algebra where you sort of try to study all the toy examples, try to classify them, and try to classify them in a unified way, preferably in the way that Salmon thought about his Flecnode polynomial. It would be great, so some of the work one reads of Segre and later is presented in a really abstract way, but it would be great if you could think about the question, what are the surfaces that have way too many lines, as a question that really has to do with differentiation along and across these lines. And then if you could try to show that anytime you have a non-full dimensional K set, it essentially has the properties of these toy examples, then you might have a kind of approach to really attacking the real K problem. This is a kind of dream of mine. Of course, what I said just didn't make any sense, and nobody quite knows how to make sense of it. So I think I'll stop here. Thanks for listening.
Are there any questions for the speaker?
So why the name Flecnode, and was that what sounded?
A Flecnode is a point which has a line that is tangent to it at 2 order 3, and I always get confused with my orders, but it's supposed to be a point where there's inflection, a node of inflection of the surface. The surface is inflecting about the same.
Do your results with Goose tell you about the structure of the minimal examples in terms of number of distinct distances?
No, they're really quite far from doing that. People would like to know, for instance, that, of course they'd like to know it's like the square lattice, but an even simpler question you could ask is, are there square root of n points on a line for an example that's close to sharp? And that is really very far from understood. In fact, I don't believe it's yet known that there are n to the epsilon when it's on a line for epsilon positive. So we really don't know what sharp things look like. Again, it's part of the same issue that we don't know what happens once we pass this Flecnode threshold. Once you're just a little bit below the Flecnode, we practically know nothing.
I don't know too much extreme combinatorics, but from what little I do remember, I think a lot of these problems have a sort of a structure randomness dichotomy, right? These extreme point sets are either extremely structured or they're like a random point set, and your talk seemed really structured, like all this hidden ruled surface and things. Would that be
Okay, well that's the structure, but the randomness is when the points are in the interiors of the polynomial of the polynomial decomposition. So the structured case is the case where, the random case is the case where where the points are in the interior. The set of points is genuinely three-dimensional in the rigid motion space, and that whole game with the subdividing polynomial was a dichotomy. It's a dichotomy between points in the interior and points on the zero set. And
so the random part is the fun of the ham sandwich.
right.
Okay.
No, sorry. I always get confused what's the bun and what's the ham, but yes, you're right. The bun of the ham sandwich.
All right, let's thank the speaker.